more frequent, intense, and extensive rainfall events in a strongly warming Arctic. T.F. Doe. S.F. Pan. Argbintanja. C. Adi Shao. First published October 3, 2022. PDF. Tools. Share. Abstract. The changes in the Arctic precipitation profoundly impact the surface mass balance of ice sheet and sea ice, the extent of snow cover, as well as the land/ice surface runoff in the Arctic, particularly when it occurs in liquid form. Here, we use state-of-the-art models from the Coupled Model Intercomparison Project Phase 5 to project the number of days with rainfall, the intensities and onset dates of rainfall events in the Arctic under the Strong Emission Scenario, RCP 8.5. The multimodal mean shows that rainfall will occur more frequently in the Arctic at the end of this century, 2091 to 2100, with larger increase in the rainy days over the Pacific and Atlantic sectors, up to 12 days per month, during the cold seasons, October, May, and over the Arctic Ocean, up to 14 days per month, during the warm seasons, June, September, as compared with the present day, 2006 to 2015. Greater uncertainty is found in the cold seasons, which mainly comes from the high variability among different models in the Norwegian Sea. 67 to 93% of the increases in rainy days is contributed by the local warming and the remainder by the increase in total precipitation. Moreover, at the end of this century, the rainfall in spring will occur much earlier than the present day by more than 1 month, and the extent of rainfall will further expand toward the center of the Arctic Ocean and the inland Greenland in the future. The changes of rainfall intensity on the Arctic land area to the climate warming are more sensitive than that on the Arctic Ocean in warm seasons, May-September. The rainfall will be further strengthened in most of the Arctic continents in summer, with the largest increase in the intensity of operator 2 mm/day along the southwest coast of Greenland. The above results are confirmed by the latest projections from CMIP6 models. Key points. The increase of the Arctic rainfall in the future performs not only in the increase in the frequency but also the intensity. Arctic rainfall events in spring will occur much earlier at the end of this century. The extent of rainfall will further expand toward the center of the Arctic Ocean and the inland Greenland in the future. Plain language summary. There is increasing interest in the response of the Arctic precipitation, especially for its liquid form, to changing climate because of their great impacts on land/ice surface runoff and the freezing and thawing processes of snow and ice. However, the spatiotemporal distribution and future changes in the frequency, timing, and intensity of rainfall events in the Arctic are poorly understood. This study reveals that the increase in rainfall in the Arctic is reflected not only in frequency but also in intensity and range. The rainfall will further advance toward the center of the Arctic Ocean and the inland area of Greenland at the end of this century, leading to more and more rainfall events in these areas. Meanwhile, the timing of rainfall in spring will be significantly advanced, taking the Chukchi Sea and the northern Barents Sea as an example. The first spring rainfall in these areas at the end of this century will occur 3 months earlier than the present day. All these trends will make rainfall a new force, accelerating the melting of snow and ice in the Arctic in the future. We further found that local warming is the main reason for more rainfall days in the Arctic. Actually, it determines almost all the increases on rainy days in the areas where precipitation phase change is highly sensitive to the temperature rise. 1. Introduction. The response of Arctic precipitation to climate warming is much more sensitive than that of global mean precipitation. Bintanja and Selton, 2014, Bohr, 2009, Trenberth, 2011, mainly due to the enhanced local surface evaporation associated with the sea ice retreat. Bintanja et al., 2020. A rapid increase in Arctic precipitation can regulate the regional hydrological cycle, impacting greatly the evolution of the ecological system. Vima et al., 2016, Rona et al., 2016, Zhang et al., 2013. The changes in amount and phase of precipitation affect the freeze-thaw process of snow and sea ice. Example, Doe et al., 2019, Purovich et al., 2017, Screen and Simond, 2012, and the surface mass balance of the Greenland ice sheet. Bring et al., 2016, Oltmans et al., 2019, Shepard et al., 2019. The increase in precipitation can desalinate the Arctic Ocean and subsequently modulate the Atlantic meridional overturning circulation. Davies et al., 2014, Katzoff and Walsh, 2000. In addition to the amount of precipitation, other precipitation variables, such as frequency and intensity, also play an important role in regional climate change. Trenberth et al., 2003, by modulating soil moisture, evaporation, and surface heat flux. Purovich et al., 2017, Chien et al., 2006, Trenberth, 2011. For example, for the same amount of precipitation in the same period, a few times of heavy precipitation events have much more serious negative impacts on the survival of Arctic aborigines and local infrastructure than many times of mild precipitation events. Example, Forbes et al., 2016, Vima et al., 2016. Moreover, the frequency and intensity of precipitation can be used to validate the cloud physical parameterization in weather and climate models. Example, Lopez, 2007. However, few studies have focused on the frequency and intensity of precipitation in the Arctic. Cohen et al., 2015. And little is known about their changes in the Arctic basin, and the projections have not yet been conducted. This study aims to project the number of days with precipitation as well as the intensity and timing of the precipitation over the Arctic, and mainly focuses on rainfall events, since it is believed that liquid will be the dominant phase of precipitation in the Arctic in the future. Bintanja and Andri, 2017, Pan et al., 2020. First, we used the ERA5, ERA interim, and MERA reanalysis data sets to validate the multi-model mean results for the present-day climate. Then, we quantified the seasonal cycle of rainy days, the onset dates and the intensity of rainfall for the future climate, 2091 to 2100. The projections were performed by the Coupled Model Intercomparison Project Phase 5, CMIP5, models under the Strong Emission Scenario, RCP 8.5, and the trends at the end of this century were specified by comparing with the current climate, 2006 to 2015. Furthermore, we estimated the contribution of local warming to the increase in rainy days. Finally, we used the simulations of the latest phase of CMIP, CMIP6, models to verify the results derived from the CMIP5 models. 2 materials and methods. The model output data used in this study are an integral part of the CMIP5 models and the latest phase, CMIP6, initiative. All data for the CMIP5 models are publicly available at http://cmip-pcmd.llnl.gov/cmip5, and the outputs of the CMIP6 models are available at https://esgf-node.llnl.gov/search/cmip6/. Daily outputs from the CMIP5 model were used for simulations with the RCP 8.5 scenario for the period of 2006 to 2100. The CMIP6 projections with the high emission scenario, SSP 585, in 2015 to 2100 were used to validate the results derived from the CMIP5 models during the same period. First, we selected the models from all available CMIP5 models for which data coverage was complete and without obvious errors and for which daily fields of air temperature, total precipitation, and snowfall were available. In total, 21 CMIP5, R1I1P1, models were used, Table 1. For CMIP6, 11 CMIP6, R1I1P1F1, models were applied in this study, Table 2. The multi-model mean was evaluated to characterize the best estimate of the simulations conducted with the CMIP model ensembles. Table 1. Description of